Good morning, ladies and gentlemen. Welcome to the second day of the International Technical Seminar organized by the Institute of Permanent Way Engineers of the Indian chapter. I hope Guwahati is treating you well. So ladies and gentlemen, at the very onset of the second day of the International Technical Seminar, I'd like to invoke Goddess Ma Kamakhya. As Assam is the land of Ma Kamakhya, Guwahati houses Ma Kamakhya's temple. So I'd like to recite a shlok for Devi Kamakhya and for you all too. Kamakhya Varde Devi, Neel Parvat Vasini, Twang Devi Jagat Mata, Yoni Mudre Namastude. So I believe Devi Kamakhya is all with us today, and we can start today's session with a smile. So I hope I see a smile in all your faces all throughout the day. Even if it's a technical session, I know, but you all are experts in your own fields. So I need not say anything else about it. And I hope that the pristine beauty of Guwahati. Have you went through the city? Of course, you all might not have got time, because I believe yesterday you all were busy enjoying the cultural program also. And I suppose it went late till night. Okay, so ladies and gentlemen, I'm Navanita, and I have been there with you from yesterday, and Pragya is with me. She was with us yesterday also. So Pragya, how are you?
I'm fine, thank you, Navneeta. I hope everybody is doing fine today after the cultural evening of yesterday night. And so I think we should begin with the session.
Of course.
So I would like to call upon the authors, presenters for the day, to please take their places on the stage. I'll call their names and I would request them to come on the dais. Mr. Anish Kumar, Director, Station Development, Engineering, Railway Board. Shri Manjul Mathur, Group General Manager, Dedicated Freight Corridor. Shri Atul P. Khare, Chief Project Manager, Tundla, Dedicated Freight Corridor. Shri A.V. Mittal, Deputy Chief Engineer, SD, Northern Railway. Shri B.P. Avasthi, Executive Director, Track. Shri A.K. Khandelwal, Executive Director, Track Machines. Shri A.K. Roy, Chief Project Manager, Rail Vikas Nigam Limited. Shri Konda Srinivas, Assistant Divisional Engineer, Bidar. Shri R.P. Tiwari, Director, Track Machines, RDSO. Shri Rahul Singh, Joint Director, Track Machines, RDSO. Shri Anil Kumar, Chief Engineer, Construction, Northeast Frontier Railway. Shri Satya Prakash Mishra, Principal, Indian Railway Track Machine Training Center. And Shri Sandeep Kumar Saha, Divisional Engineer, East, Ranchi.
So I'd like to request all the authors of the technical session 3 to come up on stage and kindly be seated. And ladies and gentlemen, the subject for this session is leveraging developments in monitoring technology for optimizing tunnel and track maintenance. Now I'd like to request Shri Sandeep Kumar, the Chief Engineer, Construction 6 of Northeast Frontier Railway, to kindly accompany the Chairman of this session, Shri S.N. Agarwal, General Manager, Southeastern Railway, and the Co-Chairman of this session, Shri A.K. Sachan, Chief Administrative Officer, Construction, Udhampur Srinagar Baramulla Rail Link Project, Northern Railway, to the dais. Thank you, sir. I now request the Chairman, Shri S.N. Agarwal, to kindly take over.
नमस्कार, आप सब लोगों को इस राइजिंग सन की धरती पर बहुत बहुत दूसरे दिन के इस सेमिनार के दूसरे दिन में बहुत बहुत स्वागत है और ज़्यादा समय ना लेते हुए चूँकि हम लोग करीब 15-20 मिनट के करीब में लेट हैं तो मैं चाहूँगा कि हम लोग तुरंत इस सेशन को शुरुआत करें। पेपर काफ़ी हैं और सभी बहुत इंटरेस्टिंग एंड बहुत ही एप्ट टू दी टॉपिक सब्जेक्ट्स हैं और चूँकि हम लोगों के पास में हम लोग करीब 15 मिनट लेट स्टार्ट किए हैं तो आई रिक्वेस्ट ऑथर्स टू kindly sum up their presentation in about 6 to 7 minutes time. 10 minutes we will leave for the last discussions and sequence also. I like slight change in the sequence. The fourth paper I like to be taken in the end. With this I call upon Shri Anish Kumar to present his paper on acoustic wireless sensor network for rail fracture detection.
मैं भी रिक्वेस्ट करूंगा कि कोई भी प्रोटोकॉल या कोई बोलने की जरूरत नहीं है, जस्ट स्टार्ट योर पेपर.
ठीक सर. Thank you, sir. The topic of this presentation is acoustic wireless sensor network for rail fracture detection. It is understood that material cry when they are distressed, and if we can somehow listen to those cry, we can then monitor the distress condition of the material. If a crack initiates in a material, then it emits high frequency inaudible elastic waves. We call them acoustic waves, and these acoustic waves propagate within the material. Now, if these waves can be sensed somehow, then the fracture can also be detected. The piezoelectric sensors are used to sense these acoustic waves, and then piezoelectric sensors are also coupled with a microcontroller which does some sort of processing to those signals, and then finally these track signals are transmitted to the nearby stations or the control stations. So this is how the fracture can be detected on a real-time basis. On the onset of the fracture, acoustic emissions are emitted. These emissions are high-frequency inaudible elastic waves within the range of 100 to 400 kilohertz frequencies. And as they travel along the material, when they hit the piezoelectric sensors, and these piezoelectric sensors are resonant to this kind of these band of wavelengths, so that their interatomic structure gets reoriented and the voltage is developed across the piezoelectric material. Those voltages can be measured by the electrodes placed across them, and this is how the fracture can be converted into an electrical signals. Then these signals can be further processed to eliminate the background noises, mechanical noises, and only those acoustic emissions corresponding to the fracture can be transmitted to the control station. This is the general schematic diagram how this wireless acoustic sensor network can be utilized in a railway system. We are having three component node stations, base stations and control station. Node stations are basically the sensors which are placed in the web of the rails, and then we have these node stations can be placed at a distance of 250 to 300 meter apart. Then over a group of node stations we have base stations. Base stations are normally 10 kilometer apart, which can cater to the node stations of 5 kilometer on the either side. So thus on a large railway network we can have thousands of node stations and about 100 of base stations, and finally the data is sent to the centralized control center. So in this whole acoustic wireless sensor network system, these are the three basic real infrastructure: node station, base station and control station. We'll see them one by one quickly. The basic function of the node station is to sense the fracture, then process the fracture data and communicate it to the base station. So for sensing we have resonant piezoelectric sensors. Then the processing is done by a microcontroller attached to it which is having limited processing power. And then finally we have a radio transceiver which communicates the data wirelessly to the base stations. Then it is coupled with a external memory, and the power setup is done by the battery, normal battery, which can last for 2 to 3 months. This is how the processing is done. When the acoustic signals are sensed by the sensor, they generate the electric signal in the time domain. Those plots are then converted into frequency domain. Then low frequency, audible frequencies are cut off, eliminated. Very high frequency, let's say more than 400 kilohertz frequencies are cut off. So we then get a signal which rests within the band of 100 to 400 kilohertz. Now, acoustic emissions can be due to metallic fracture also, and can be due to mechanical factors also, like impact, hammering, friction. So here all those acoustic emissions coming due to mechanical sources are also eliminated. And finally, the signals which corresponds to metallic fracture are only processed and transmitted to the base station. This is the flow chart. First, the electric signal in the time domain are converted into frequency domain using fast Fourier transformation. Then the band filtering is done, that audible, low frequencies and very high frequency signal are eliminated. Then within the acoustic emissions range 100 to 400 hertz frequencies, the microcontroller are having pattern recognition software which do the cross correlation, and the signature pattern of mechanical sources and metallic fracture both are different. So it does the discrimination and eliminates the emissions coming out of mechanical sources also. And only fracture which are due to metallic cracks are finally processed and sent onward. So most of the processing is done at the node station itself, but few more processing are done at the base station, since base stations are having larger storage capacity and they cater to a number of nodes. So base station does the continuous monitoring of the fracture. It counts the cumulative signals, and right from initiation up to actual happening of the fracture, it contains the data. And the second most important processing at the base station that is done is the finding out the location of the fracture. If a fracture happens, it is sensed by adjoining sensor, and based upon the time delay of the data coming from those two sensors, it can sense the location of the fracture also. And the communications are all wireless. Node station to base station communication is done by 3G or GSM system because they are within the range of 10 to 15 kilometers. And base station to control station communication is done by the satellite communication system. These are the few advantages, that it is continuous real-time fracture monitoring. Initiation, propagation of fracture can all be monitored. This can detect the location of the fracture also, but of course size or shape of the fracture cannot be determined. And it has tremendous scalability inbuilt in this system. The node station, which does the most of the processing, can take sensor data from variety of sensors. Like if we have a sensor for the wheel monitoring, or if we have a sensor for the signal spec monitoring, all those data can be coupled and processing can be done for the intended purpose at the node station itself. And all data are encrypted, so data confidentiality and integrity is 100% maintained. Thanks.
Thank you, Mr. Anish Kumar. A very interesting paper on subject which is yet to start on Indian Railways. And now I call upon Mr. Atul Khare and Mr. Mathur for presenting the paper on pre-tamping survey using survey trolley and in design mode tamping using absolute profile on DFC corridor.
Very good morning, and I'll be talking about the pre-tamping survey using the survey trolley and the design mode tamping using absolute profiles on the DFCCL corridor. On the Indian Railways, traditionally the geometry correction has been done by relative measurements by taking the signs on the overlapping chords, and the error is then distributed among the adjacent station. With the advent of with the use of the tamping machines, we have started using the smoothing mode of the tamping and the alignment correction was a bit sophisticated compared to what we have been using earlier. But the challenge is a design mode tamping, and we have been talking about the design mode tamping for the last about more than a decade. And the challenge there is to find a simple way by which I can measure the ground measurements and then generate a feed for the tamping machine. Now this can be achieved by using the survey trolleys. These survey trolleys have got the capacity to capture the ground measurements and then convert them into a feed which can be readily adapted by the tamping machines. So we have tried this survey trolley solution on the Bahupur Khurja or the Kanpur Khurja section of the DFCCIL, and I am presenting the case study here. This is how the proposed trolley system looks like, and you can use one trolley or the two trolley. These trolleys are lightweight, they are about 20 kg in the weight. It can be easily lifted by one or two men. It can also be pushed on the track with the help of one or two men. It has got a spring-loaded gauge sensor which will measure the gauge. It has got a calibrated inclination sensor which measures the cant, and it has got an odometer which measures the distances. When you use the two trolley, one of the trolley is called the instrument trolley, and this instrument trolley has got a robotic total station. The other trolley is called measurement trolley or the prism trolley, and this prism trolley will carry the prism and a control unit. Now this is how a robotic total station looks like, and it is called a robotic total station because once you sight a prism with it, it gets glued to that prism. So as and when the prism moves in forward or the backward direction, it will swivel along the vertical axis to keep itself always connected with this prism. This can be mounted on the trolley, or it can also be put on the side of the track on a separate tripod. There is a control unit, and this control unit carries the data of the design profile. And it is here that the design profile is compared with the measured profile and the slews are calculated. There is a radio communication between the measurement trolley and the survey trolley. And this is how the measurement trolley looks like. It has got a handle and a brake, basically 3 wheels. It can be pushed on the track. But the important parts are circled. The one is the cant sensor, and the cant sensor, if you see on the right hand side, is used to measure the cant. The gauge sensor is used to measure the gauge, and an inclination sensor is used to measure the inclination of it. Now, if I know the position, absolute position of the prism, you can see on the right hand side figure, the XYZ coordinate of the prism are known to me, then by using a little geometry and mathematics, I can calculate the absolute coordinates of the left and right rails, which are x1, y1, z1, x2, y2, z2. Now, how we do it? This is a general survey system that we use on the construction project. There is a primary network where the control points are stationed at a distance of about 1 to 1.5 kilometers. And there is a secondary network where the control points are again at a distance of about 150 to 200 meters. And then we carry out the DGPS survey on the primary control points to get their x and y coordinates through the DGPS instruments. This is then connected to the secondary network with the help of the horizontal traversing. And you determine the levels of all these points by connecting them with the nearest GTS benchmark. And then carrying out the topographic survey, we work out the various profiles of the track, the formation levels and all other things. But the important thing here is, once we do the survey and we construct the track, this complete survey system can be preserved. And it can be preserved to act as a ground reference for subsequent maintenance interventions. Now, this is the basic principle of the survey trolley. The design profile is fed into the survey system, the survey trolley in the controller unit. As-built profile is measured with the survey trolley, and then delta, the difference between the design and as-built profile, gives the slews or the uplifts and whatever parameter you need for the tamping machine to do the alignment or the cross-level corrections. Now, this is the true trolley system. As you can see, I have shown in the middle the controller unit. This is the instrument trolley. It's an animation. You can see the instrument trolley moves forward onto the first control point, and it will measure its coordinate. The instrument trolley then moves to the second control point, which is about 150 to 200 meters away. It also measures its coordinate. Now, by doing so, you are establishing an optical chord, and this chord is used to determine the measurements of the intermediate points, and you will see the measurement trolley then moves and it calculates the coordinates of the various points. Joining these measurements points, you can get the as-built alignment of the track. And this as-built alignment of the track is actually then compared with the design profile which is fed into the machine to determine the sluice, and the sluice can always be processed with the help of the computer in a format which is compatible with the track machine, and it can directly then do the design tamping. And this is the system of single trolley where you use only one trolley. The survey instrument now is not mounted on the trolley, it is placed by the side of the track. And same robotic total station is used. So by taking the measurement to 3 control points, you first determine the position of this robotic station by the method of resection. Then this robotic total station is used to size the measurement trolley, and once it sizes the measurement trolley, it calculates the coordinate of this trolley. And then the trolley is pushed forward, and the robotic station will again swivel on the vertical axis to keep itself connected with the survey trolley, and it will calculate the XYZ coordinate of all the measurement point, and it will give the as-built alignment. This is how the output of the machine will look like. It will give the lift, it will give the shift and the other parameters. This can, as I said already, this can be processed on a computer, and you can actually generate a feed for the tamping machine in the format you desire. And these are the results before tamping and after tamping of the work carried out on the Kanpur-Khurja section. Now the key benefits is that these trolleys are lightweight and they can be easily lifted off the track. They reduce the tamping time and the cost because the machine will quickly capture the ground parameters and convert them into the feed for the tamping machine. The maintenance time, here I want to say that the track position is becoming increasingly difficult for the engineers, and it is the quality of the maintenance attention which will matter to us. If you give a quality maintenance attention, then the frequency of the attention can be prolonged. You need not give the maintenance attentions frequently. And these survey systems develop a permanent repository of the track alignment which can be used for the subsequent maintenance interventions. So the initial quality of the track determines the life. It also affects the frequency of the maintenance intervention. Through use of the absolute profiles and using the design mode tamping, the maintenance inputs can be delayed, and absolute track geometry provides a permanent reference for the future maintenance of the track. And at the last, I would end my presentation with this popular adage which says that the bitterness of the poor quality remains long after the sweetness of the low price is forgotten. So we should look for some technologies which will give us a good quality of the work rather than looking at the price of it. And I also take this opportunity to invite all the PV engineers available here to the DFCCIL project. A host of new technologies are being introduced on the DFCCIL projects like mechanized construction of track, mechanized construction of the OHE, canted turnouts, RE walls, etc. And it will be our pleasure to take you to our construction sites. Thank you.
Thank you, Mr. Mathur and Mr. Khare, for this very practical paper on design mode tamping using the trolley. Now I invite Mr. A.V. Mittal for his paper on real-time detection of rail fractures.
Good morning, sir. I'll just take you to this is the team, our team who have done the study on this topic. I have structured my presentation in this under 5 heads, so I'll be taking you through to the initial 2-1 and will directly come to the main proposed concept and its advantages. Yeah, these are the existing systems: visual inspection, static, non-destructive testing, then using SRT, DRTs or disturbance to track circuits, and the non-conventional concepts which are being tried are use of two impedance connections or LED LDR assembly. A system is also being tried using cameras mounted on the underframe. As due to rail-wheel interaction, vibrations are transmitted on the rail. If this is the vibration, and if we have sensors installed at some distance apart, then the signal which is transmitted will be something like this. In case of unfractured rail, the amplitude of the signal will be relatively low,